Hello and good morning, or good noon, or good afternoon, wherever in the world you are. Welcome to the second part of BlackHoodie. And yeah, allow me just for a second to adjust all the settings, which means mostly fixing up the focus of the OBS application. Perfect. Scene one. Okay. Hello, here we are. I see the good mornings in the chat, which means you guys can hear me, which is awesome. Yes. This is the second time I'm streaming stuff, and it's still weird to talk to my computer. So apologies for any funny faces I'm making while staring at my screen and trying to make sense of things that I'm seeing. So I've been watching the first part myself at home, and yeah, I followed the stream along, and I realized that in the first class we went a little slow, mostly because I was thinking more than I was talking. And that usually is all right in a class with people where we have 2 days. But since, as mentioned, we only have 8 hours here, I really want to pick up speed today and push the topics through a little bit faster. That mentioned, there is a risk of losing some people on the way, but don't worry, unless like a real world class, you can always review this class. So you can go back to my Twitch channel, and the Twitch will stay up there for I think 60 days, and I will eventually push all the streams to YouTube. So you can watch it as often as you want. If you don't understand something, you can go through it and do your exercises again and again. And that's typically how people learn, by repeating and repeating and repeating and repeating. Also, something I forgot to mention last time, my Twitter DMs are open. So if you have any questions that come up during the class that I do not answer, or that you post in the chat and that I still do not answer, then please feel free to send me a Twitter DM. I'm happy to answer any question that comes in. I'm usually not the fastest with answering my DMs, but since this class is happening right now, I'll do my best to actually catch up on questions. Okay. That all said, let's jump right in and get going because we're on a tight schedule, right? So, one more thing I wanted to say. The slides are like, I might have said it before, they're like scratching the tip of the iceberg. They're really just like the most important stuff. And my thought was that we push the slides through as fast as possible and then spend the rest of the time in tools. Okay, that didn't work so well because I got caught up in the slides and we're still not done with them. Which is fine too. Last time you saw a little bit of how a hexadecider looks like, how a binary in a hexadecider looks like. You saw at least one screen of the IDA Pro debugger, which is something we're going to be working on. We're going to be working with next week. And you learned a bit about the registers that are used in 64-bit Intel architecture, like the most important ones. And today we're going to be looking at stack and heap and function stack frames, and eventually control structures in the binary. And I hope that eventually we spend all of our time in the exercise binaries that I put up on GitHub. If you're here for the first time, or if you haven't downloaded the materials yet, please navigate to, I'll show you again, the GitHub where I've been hiding all the class materials, which is github.com/BlackHoodie RE/BlackHoodie virtual, BlackHoodie_virtual. Most importantly, what we will be needing today is the virtualbh.exe and the virtualbh.c file. Okay, back to the slides. Here we go. So next chapter, memory. Memory is a big word, and there's lots of different kinds of memory in the computer, including inside of the CPU, and we're not going to be nearly talking enough about all of them. Literally, there's stacks of books about different kinds of memory, like cache or the RAM or virtual versus physical memory. So yeah, if you're interested in that particularly, I recommend get yourself some reading material. Again, just the most important bits here. Something that is important and shall be mentioned in the class, but probably won't give you very many headaches while reverse engineering a binary, is the data endianness that's common in Intel architecture. You might have heard about big endian and little endian, which literally just means from which side do we read byte stream. And this is something odd. Thankfully, the tools that we're working with usually represent memory in the correct order so that we can just read the content of the memory. But in reality, on Intel architecture, memory is organized in the reverse way, which for us is mostly visible when we look at stack addresses, because our stacks grow from the bottom up. So as you keep stacking memory, as you keep stacking values in the stack, the addresses of your values in decrease. Sorry, decrease. Yeah, it keeps being confusing even if you've worked on that architecture for a while. And yeah, you'll see more about the stack in a second. What exactly does little endian mean? Little endian, if we look at bytes, means that the most significant byte is the last one that we see in the stream, and the least significant byte is the first one. So if you look at that graphic down here, it explains it pretty well. Big endian is big endian sorts the bytes, or like displays the bytes in a way how most of us are used to reading books. So first letter, second letter, third letter, etc., etc. And little endian reverses that byte order, which means last byte first, second to last byte first, third to last byte first, and so on, until we get to the first byte, which is in the last position. Really, for me, I don't recall when exactly that comes up in reverse engineering tasks, but where that definitely is something you need to watch out for is if you want to develop exploits or like write your own bytecode, essentially. That's where this can be very painful. All right, so far so good. Again, there's a link on the slide if you want to learn more about the topic. I personally think it's not the most important thing to learn when you start reverse engineering. This topic, though, executable file formats, is a lot more important. And it's big and complicated too. Let me see, where do we start here? Your operating system, and in that case, it doesn't matter whether you're on Linux, on OS X, or on Windows. They recognize executable file formats as files that can be executed. Haha. More specifically, as files that can be loaded by a loader, projected into memory, and then executed. All right, I'm repeating myself. In other words, like for example, if you have a graphics file like a PNG, if you double-click a PNG, what happens? If you double-click the PNG, you open, like your computer, your operating system knows an associated application that can display the PNG to display your file, but you don't execute the PNG, if you see what I mean. You open the PNG and you display it. If you have an executable file, like on Windows, for example, you look at Microsoft Word, word.exe, that's an executable file. So you double-click Word, and then what happens is that your Windows loader recognizes that file, reads the header, and based on the information of that executable file header, projects the file into memory. Let's jump ahead for a second so you understand better what I mean here. Better or worse, I'm not sure if this explains anything, but we'll see when we start debugging in IDA Pro that you can start your process, and then when you look at memory, IDA gives you this beautiful memory map. What you see in front of you is a running process on Windows. That means that the parts of the executable on disk. So imagine imagine when we looked at the hex editor, that was the insides of your executable file that you have on your hard drive. When you double click that executable file, the loader takes the file, looks at the header, looks at like where is the code in there, where is the data in there, and takes those different pieces and maps them into memory. Once they're mapped in memory, they look like this, more or less. You can see this faintly highlighted gray line where it says text. That's our code section. That's where the executable code ended up in memory. You know that that's executable because if you follow the line, where's my mousey? If you follow the line, you eventually see an X. This X here. Here is an R, that means readable, and the X means executable. There's a dot in between where a W could be. So the W stands for writable, and if you know a bit or other about security, then you rather wouldn't want a writable executable code section. All right, other things we see here is iData, RData, data, and pdata. That's different types of data sections that the executable can come with. We won't talk about those details here. And then at the top of the page, you see a stack. And believe it or not, the rest of what you see here, like all the sections that are called debug, no, that's our heap. So there isn't like one chunk of heap. Yeah, more about that in a second too. But there is one chunk of stack, the stack memory, and that stack belongs to a thread. Yeah, more about that too. Then, also important, at the bottom of the page, you see msvcr110.dll. That's a loaded library that our process uses. More about that later on too. Back to the file formats. For us, important to take away from what I was just ranting about is that if we do static reverse engineering of a file on disk, like you load your executable file into hex editor or into IDA Pro, then what you see there is the file on disk. The file on disk is not the same as the file in memory. In in-person classes, I usually spend a great deal of time on hammering that into people's heads that if you load something into a debugger, it's not the same thing as what is on disk. That is sometimes hard to understand. So that becomes important, especially if you want to change an execution flow. Like you sit in your debugger, you want to change what the binary is doing at runtime. Like there is a branch, an if else, if you want it that way, and you want to debug the left branch, but the execution will go to the right branch. Then you go and patch that execution flow so you can debug the left branch. And what you're doing there is you're modifying this part here, like memory that's in this range where the text section is located. You don't modify the file on disk. If you want to modify a file on disk, you use your hex editor, which is slightly more confusing because the hex editor doesn't show you disassembly and you have to find the address in there and find the actual byte that you want to flip and so on and so forth. But yeah, otherwise, what happens is that your changes do not persist. So yeah, we'll look at that again in the debugger. Now, about file formats. What exactly is a file format and why does it matter to us? A file format is important for the loader to understand of what to do with the executable file. And for us, it's interesting because there's some nice data hidden in the header of an executable file. Overall, there is a couple of different executable file formats. There is the Windows PE, the portable executable, which is the one we're dealing with in our class. There's the Linux ELF, which is also very popular, which in my opinion is slightly like a tiny bit more chaotic. It's beautiful, and don't get me wrong, it's very flexible and extendable, but it's a bit harder to understand than PE. Yeah, then there will also be Windows COF files, and there's a couple others that are much less popular. Anyhow, for us, it is time to fire up a tool, namely the Cff Explorer. So if you're following along, please start CFF, which looks very boring if there's no executable file in there. Very empty, which is why we want the virtual bh.exe to be opened in our Cff Explorer. By the way, in the morning, I usually have trouble speaking proper English, which is why this morning I did some practice on how to, articulate myself. And now the words are flowing. I'm very happy. Okay. So Cff Explorer is like from the Stone Ages. It's been a thing long before I touched my first binary, and it probably will stick around for a while longer. It's very simple, but also very effective. Cff Explorer shows us the executable file handler of Windows PE files. Now, what is important is the tab on the left side where you see the different parts of the header listed. The different parts of the header, what do I mean by that? So first and foremost, comically, there is a DOS header. And if you remember Windows DOS, that was decades ago. And for compatibility reasons, and meanwhile, I also think for nostalgic reasons, Microsoft has kept the DOS header around for years and years to come. So there is still a DOS header in every executable that any Windows compiler spits out. It's just not used at all. If we click on that, there is values in there. There's a magic, the 5A4D, which if you look at a lot of PE files in a hex editor, you'll see that value a lot. 5A4D stands for MZ. That's a funny story, actually. Should I show you that too? Oh, I have HXD still open here. Let's do a very short history class. I'm switching to HXD just because I wanted to show you the MZ. If you look here, the first 2 bytes of our executable for D5A. Oh, there's actually, this is a case of little endian. Wait a second. The first 2 letters or the first 2 bytes of each Windows portable executable since portable executable was invented are MZ. And they're actually the initials of a Microsoft engineer, the guy who came up with the P format. Like, I don't want to tell you something wrong. He made some important contribution, let's put it like that. I think the M stands for Mark and the Z, I really don't know. But yeah, look it up on Wikipedia. You'll find a very nice picture where the guy's like smiling. It's actually kind of funny. Okay, and something I just noticed that's interesting, if you look at the bytes here, it's 4D5A, right? Then, if we quickly look back at CFF, here we are, then you can see that in here the bytes are 5A4D. If you compare that with the hex editor, it's reversed, right? Here we became victims of the little endian on Intel architectures. Weird. Okay, whatever. The other values inside of the DOS header are really rather uninteresting. As we move on, we have the NT header, which comes with another signature. Here's the value 4550. That is actually 5045 and stands for PE. So this is where the PE header starts. Before the PE header is the DOS header and the rich header, but we won't go into that detail now. The PE header where it starts getting interesting for us. Yeah, why the tab is called file header, I have no idea. In the next tab, we learn that we're looking at a 64-bit binary, which is set here. By the way, you can also modify data in there, and you can For example, try to teach your file that it's not a 64-bit Intel executable, but MIPS 16-bit. Wouldn't help you much because it wouldn't execute anymore, but just so you know, CFF is an editor, so you can totally modify the data in there, which is interesting in the sense, like, for example, if you look at this field here, where it says timestamp, there's a value in there. That's a hex value, but if you parse that into a date, you will get the compilation timestamp. So your compiler compiles the binary and notes in the header of when that happened. That's nice if you develop an application and you lost track of what's the old version, what's the newer version, then that could come in handy. I've never done that either though. Another situation where this field is very interesting is when you analyze malware. Like you're following one specific actor or one specific strain of malware, and you want to see what's the older versions and how did they develop over time. And this timestamp is very handy. On the other side, if you're a malware author and you don't want to give that information away, you like do this, and essentially, uh, yeah, you modify that timestamp away, and then you save the file. Then the timestamp would be gone. Yeah, this much. And also what's interesting in here is the characteristics, which is a quick and dirty way to figure out whether your file is an executable or a loadable library. And we will be talking about the difference of these two at some point. How did I open that tab? I just clicked where it says click here, then you see the file characteristics. All right. Whoops, go away. Then, as we move on, another interesting field in the Cff Explorer is the address of entry point, which we see here. Again, you could modify that, but if you modify the wrong things in the header, then your file won't execute anymore. Also, I never looked in the details of this, but I think IdaPro, or like the disassembly tools that we're using, they rely on the header information in order to figure out where is what inside the binary. And yeah, if you would be editing the header away, then your analysis tools would probably not be happy with you. The address of entry point is important because it tells us where in the binary execution starts. Now, if you like reverse engineering a web browser, that information is not very helpful. But if you're looking at a small executable, say malware is usually not that big, then you might be interested in like, what are the first couple things that the binary is doing once it's executing? This is, yeah, especially with malware, that's interesting to see like all of the executable path when the thing is executed, as opposed to like bigger applications where this is rather pointless to analyze. Then another thing that is interesting is the subsystem where it says Windows Console. And if I click here, I get different options. So for example, there is the Windows GUI, but there's also native. There's OS2 and POSIX. Subsystem, yeah, we won't be going into details of subsystems, but your Windows understands different environments to execute executables. One of the newer subsystems that's not in here is Linux on Windows. I forgot what it's called, but yeah, that's missing here. Anyhow, our executable expects to be executed inside of a Windows console environment. And again, we could change that here, but if we change that, the binary would not be executing anymore. DLL characteristics, that's bullshit because we don't have a DLL here. Okay, I think that is it in the optional header. Then this we can ignore for now. What is very, very important and very, very interesting is the section header. The section headers describe where our sections, like the different important parts of the binary are located inside of the executable. So here you see something that you saw before in the memory dump. On the very left side, there's the name of sections. You have a text section, rdata, data, pdata, resource, and reloc. Text is the one and only executable section in this binary. How do I know? If you follow me, in this line on the very right side is a concept characteristics. There's a 6 there. Now I've looked at a lot of binaries, which is why I know the 6 tells me it's executable, but there is a cheat sheet too, which you can get if you sorry, let's do this again. If you right click, it says change section flags. We don't want to change them, we just want to look at them, but that's here the same thing. Where you see there is a tick in the box is executable and the tick in the box is readable. No tick in the box is writable. So here is our one and only executable section. You can do the same thing on the other ones and you'll see that they're readable, or they might be readable and writable, like this one where the C is standing, but they're not executable. We could change that here as well if that's the thing you want to do. All right, so this is how a section layout looks for a normally fresh compiled binary. Where this layout becomes interesting is if you're trying to spot packed binaries on Windows. Runtime packers and encryptors often change, modify, and scramble the section table. There it's common to have more than one executable section if the thing is packed. It is also very common that the names of the sections are changed. It is sometimes common that you have a large section, but it's empty. If you look down here, there is like a little window that shows you the content of a section, which is rather unexciting for our kind. But if you look at the section and it's completely empty, like just full of nulls, that's something rather suspicious. Maybe not that suspicious. Anyhow, if you something to be said about the table too is that this is up to the compiler. The Windows loader only looks at these characteristics like the flags and the sizes and like basically everything that's numbers. It doesn't care about the names of a section. So if you have 5 text sections in this binary, it still doesn't matter as long as only one of them is executable, then only this one will get the executable flag side in memory. And yeah, depending on where the entry point points at, their execution will start to roll. I'm saying this because depending on different compilers, you might get a different section layout that looks confusingly different to this one. Especially if you look at, I believe .NET binaries look kind of funny. Don't remember, but yeah, if you look at a lot of different binaries in Cff Explorer, you will see some funny things. Good. For us, important today is only that we have one section that's executable. It's up here, the .text, and we see that because there is a 6, the first number in the characteristics. Good. Then, what else is interesting? The import directory, something to be talking about very quickly. What are imports? So if you're writing an application and you use anything that comes out of a library function, like you import standard IO and then start calling printf, or like you operate on files, you call file open and then file read and file write, and yeah, these kinds of APIs. Like basically anything that allows you to interact with the operating system. That will require a binary to import APIs that define that interface. Now, this is leaning out a bit further. Your operating system is basically there to provide services to executable applications. So your operating system manages memory, your operating system manages the file system, it manages the screen, it manages extra memory like USB sticks, it manages the mouse, and your application gets to interact with these components. So Again, if you want to open a file on disk, your application needs to ask the operating system for a file handle. This is what we do with APIs that eventually issue system calls that interact with the file system driver in the kernel, which then produces a handle and gives it back. Long story short, if our application wants to interact with the operating system, we need to know about these interfaces. You need to know about the API calls that allow you to issue these certain system calls to get what you want. If a system call is what gets you the resource that you want. Anyway, there's different cases. But yeah, for us, what's important today is the executable file knows which APIs it needs. And based on that, it defines an import table which says which libraries to import. Most interesting and important APIs on a Windows for a Windows application that most common tools need are located in kernel 32.dll. Actually almost all Windows executable files list the kernel 32.dll as import because it's also used to set up the application in memory, but that's a different story. When you click on one of those imports, you see which functions have been imported from that library. It is important to note here as well that that something is listed in the import table doesn't mean it's actually used in the binary, and that something is not listed in the import table doesn't mean it cannot be used in the binary. Like you can dynamically load libraries and you can dynamically load APIs out of those libraries, and they do not have to be listed in the import table. It's something like some malware analysts sometimes resort to just look at this list and say like, oh, I see network APIs and I see file system APIs, and hence this is exactly what the binary is doing, and that's just not how it works. However, if we look at a benign binary, especially one that we compile ourselves and we know that it does not hide things, then we can look at those functions and see, for example, that string len is called in the binary or that the printf is called in the binary, and it will be very true. Okay, this much about the imports. If we were looking at the binary, we would have an export directory as well. More about that later. The rest in here is interesting to study too, but out of scope for us. Good. This much about the Cff Explorer. Oh, and by the way, on the first side, on the first tab, you see, again, we have a portable executable, 64. It says it's a DLL here, which is not true. It tells you when the file was created, which is not the same thing as the compilation timestamp. And it tells you file hashes like ND5 and SHA-1 about the file. So yeah, for a malware analyst, Cff Explorer is really, really nice. All right, this much about executable files. OBS. Bring me back to the slides. Here we are. Good. On we move with assembly. First though, since I keep talking about IDA Pro and all the tools and how they work, maybe let's have a quick excursion into IDA Pro and actually look at a binary. Therefore, zoom me to IDA Pro. Here we go. So I will ask you to open up the IDA Pro freeware I asked you to install. By the way, we can only use this for the class. IDA Pro freeware cannot be used for any commercial purpose. Yeah, if you start IDA Pro, it will ask you which file you want to open. And if you say just go work on your own, you get this empty screen. In there, we get to drop whichever executable we want to analyze. So I just take my .exe, the virtualbh.exe, and throw it into IDA Pro. Then we get this beautiful screen which says load a new file. Yes, we want to load a new file, and all the default settings in here are pretty much perfect for Windows PE files. Altogether, IDA's auto-analysis, like all the default analysis that IDA Pro can do, they work very well on Windows PE. They work kind of well on Linux ELF. If you look at the different architecture and a different file format, IDA Pro still does a good job, but might be slightly confused on occasions of like how exactly to parse a given header or how exactly to disassemble stuff. Other than that, if you just click OK and let IDA Pro run, it does an almost perfect job on this executable. Welcome to the world of disassemblers. We're inside of the binary. Not exactly though. So what IDA Pro does is it opens up the executable, it analyzes it, and creates a representation in the form of a database. The thing that you see in front of you is not the actual file content. That's a little tricky to understand. It is IDA Pro's representation of the executable file. I'll just leave it at that. And why I'm saying this is an almost perfect analysis of the binary is because there is a little glitch with this thing where I really don't understand of why that error happens, but it's interesting. If you, oh, by the way, you can scroll in and out if you click, like I'm sure it's the same for you, but if I click Control and then scroll in on my mouse, I can get closer to the actual disassembly. And first things first, what I want you to do is click on this thing where it says cleanup, press N for naming, and remove the name. Enter. Then we have a better name. IDA Pro's auto-analysis tries to find known functions and give them names. That becomes visible if you look on the left side. Here's a list of functions in the functions window of all the functions that were found in this mini executable. And some of them have names. Like, for example, here's like, this is a string import. Here's a start function, which is where the entry point is pointing to. You have different other functions that I've never heard of before, and a lib name, and so on and so forth. So yeah, IDA did a good job in renaming those into something where it thinks this function is adhering to the name. Like it names the function in a manner where it thinks that this function is exactly what IDA Pro thinks. Again, though, IDA Pro just thinks, and sometimes IDA Pro is wrong about that. Big magic revelation: most binary analysis tools are occasionally wrong about their analysis results. This is very, very upsetting if you don't know what you're looking at. Like if you're a beginner and you expect the tool to show you good assembly, like good and sound function where everything that needs to be there is there, and the disassembler doesn't show you the whole function or shows you instructions that are wrong, like parses data instead of an instruction, and all of a sudden everything's mangled up. And that is very, very confusing when you're just getting started. That said, I keep teaching with IDA Pro because in the quality scale of output I have seen from IDA Pro, it has good quality. Like the output assembly is usually what the binary contains, like the mnemonics here match the bytecode. And the auto analysis of IDA Pro takes people directly to the main function. The renaming of library functions works fairly well, and the tool is very intuitive. That doesn't mean that IDA Pro is the very best of all disassembly frameworks. There's others out there, especially Ghidra, that show a couple different features and also show very good assembly quality. I just think that the intuitive GUI, like the clicky stuff that IDA Pro offers, is slightly better, especially for people who are just getting started. I'm talking in circles. What I just did here by renaming that function, or like by deleting the name, was fixing a misinterpretation. And I spent a lot of time talking about how good IdaPro is, and the first thing I did was fixing a bug, which is interesting. In a second, we'll be looking at what's inside of that function, and then we can wonder together of why analysis thought it's called cleanup. Oh, actually, if you put your mouse over a function, you get this little pop-up which shows you what's there. It shows you more than what's there even. It shows you the whole stash of assembly that's in there. Anyhow, for us, this is just like a quick snip in there, and you'll recognize the function that you see in this pop-up. That's the little hello world, or almost the little hello world that I showed you in the very first class. Yeah. And IdaPro's auto analysis thought that this is a cleanup function. I have no idea why. Anyway, we fixed it. Oh, I just see in the chat that OBS isn't capturing any pop-ups. Apologies, that is very upsetting. Happens. You just have to listen to me. So when I say move your mouse over a thing, I'll need to say which thing, and you will see the pop-up just like I do. Let's try this for a second. So you have this very first function here, 14.000.1250. If you have IdaPro open and you move your mouse to hover over that function, you should see a little yellow pop-up come up. It's just like a window that sits there. The same happens if you move your mouse over any other function. Like a little pop-up appears and you see what's inside of that function. That's very cool if you have a tiny binary and you just want to get quick look at what a certain function does or what's inside of a certain function. Not so much if you look at a big binary. Anyhow, so everybody's still with me. What was I gonna do? All right. IdaPro 101. In front of us, we see the infamous graph view. The graph view shows us a binary function graph. Just to show you what a nicer graph. Oh, okay. If I click on one of those functions that's a little bigger, we see something like a bigger graph. We get to that too, don't be confused. The graph of our main function is rather boring because it's just like one box. But usually that function, if there's branches in there and switch cases and loops, that should be bigger and more graphy. Important for us, the graph view can be changed to text view. So there's graph view and text view. And if you press the spacebar, view changes to text view. Text view is sometimes nice because you can see the addresses, like the virtual addresses of your functions and specific instructions in the binary. And what's also good about the text view, which I like very much, is that we can configure it to show us the code bytes. Follow me for an instant. Let's go to the Options tab and click on General. And in there is a field that says number of opcode bytes. You see that here where I'm moving my mouse, number of opcode bytes. And it specifically says non-graph. You can tell IdaPro to show you 6 should be a good value. Let's do 8 for introduction. You can tell IdaPro to show you 8 bytes of an opcode. If the opcode is 8 bytes long, then I say OK. And dum, all of a sudden we have like these blue bytes written here. Yeah, welcome back to the bytecode. So these bytes here are what this function looks like for on disk or like in the byte stream. We quickly saw this the other day when I showed you the debugger screenshot. But anyway, okay, now so you have the tool in front of you yourself and can appreciate the bytes themselves. By the way, the highlighting function in this tool, like, is something I really like about IDA. There's a lot of things I really like about IDA. It's just so self-explanatory. Anyhow, if you click on something and IDA Pro finds another representation of the same thing, doesn't matter what it is. If it's like a variable name, it's like a number. If it's an instruction, if it's an address, IDA Pro will just highlight wherever it finds it on the screen, which can be very handy. All right, and with a tab, we get back to the graph view. There is a miniature graph view on the bottom. By the way, there was like a command output box down here that I immediately closed. That's very handy if you write scripts and want to debug analysis, which is not something we're going to do in this class. Yeah, this graph overview here can be interesting if you look at a, oops, sorry. If you look at an actual graph. So here you would see where the graph is, and with the dotted line, you see where your screen is pointing to. Anyhow, back to the function list for a second. So the turquoise, or like the green bluish functions in here, are actual code in the executable. So like, just as an example, if I double click on the pre-C init in here, I get to another function graph. Here's code. I specifically say this because if you look at the ping function, for example, here's stringlen, which is something that's called inside the binary. The ping functions are imports. If I click on that, I don't get anywhere. I see like one little stub that has a jump instruction, and I see an offset that's called imp stringlen, which is like import stringlen. And this is not going anywhere. You can double click on it and you get to the import table. About that import table in a bit, not to confuse you. So yeah, that's the difference between the blue and the pink entries over here. Altogether, this list is just there to show us what is there. And you'll have noticed in IDA Pro, you can just double click on things and you'll get to places. By the way, the way to get back from places is escape. So if you double click on a function and you want to get back to where you just came from, you click escape. And escape works multiple times too. So if you walk down a function tree and you don't know how to get back, you just click escape, 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 escape. Good. Navigating that GUI is a bit of a ramp at the beginning to learn all the shortcuts, but once you get it, it's really, really good. What else? Oh yeah, the different tabs. So we have the IDA view, which is generally the disassembly. And then we have the hex view, which is the hex representation. Before I said if you modify stuff in memory, that's not something that's persisted into the file on disk. And in IDA Pro, we look at another trickery. If you look at this representation of the hex inside of the binary, this is actually the database that IDA Pro produces. Not to be telling you something wrong now, but I'm fairly sure if you modify the hex inside of that hex view, it does not actually change neither the file on disk nor anything in memory. Yeah, this much said, but if you modify stuff in here, like if you modify bytecode in here, the assembly out here changes. Should, anyway. In that hex dump, we see, of course, executable code. Do we also see data? Oh yeah, down here is like uninitialized unknown stacks, and this is one of the data sections. Oh yeah, the reason why I said last time I love to stare at hex dumps is because you can find things in there, like a strings table, where if I just scroll up and down this hex dump, I find the hello world string. It's, by the way, located in a data section because it's data. Then you see something that says addition, multiplication, division, such string, much wow, found, 1, 2, 3, 4, 5. So yeah, there's a couple of Easter eggs hidden in here that we're going to analyze. Yeah, and you can scroll up and down, you'll find some debug prints. By the way, there's lots of strings in an executable binary that the compiler puts in there that might never actually be used by the code you have written, but they're still inside the binary. Which is interesting, like some malware analysts work with strings that can be found in an executable file. And it so happens that, I mean, depending on the size of the application and how many strings are actually used in the code, but depends that a considerable chunk of strings, like readable strings that are found in an executable file, have nothing to do with the code flow whatsoever. It's just like CRT set unhandled exception filter, which doesn't tell you anything about the malware, but whatever. Yeah, and if I scroll back up, I get back to the executable code. How do you know it's executable code? If you stare at a couple of hex dumps, you'll know what looks like bytecode and you'll know what doesn't look like bytecode. That is a rather stupid thing to say for me, but I really don't know how to better explain. It's like the level of variance of bytes in the code, then the occasional null byte in there. If you look at the distribution of null bytes, this looks like a normal distribution of null bytes. If you look at the hex dump of a packed file, like a crypted file, the distribution of null bytes looks slightly different. Usually, in most cases. Yeah, with a little experience, these bytecodes will look more familiar to you than you might know. Anyhow, I love hex dumps. Love them. What else did we want to look at? The imports. If you follow me in the tabs up here, there's a tab that's called imports. In there, we see a very short list of imports. If you look at the bigger application, this list like contains hundreds and hundreds and hundreds of entries. Again, we see the libraries that the application wants to import, which by the way is a job of the loader. I talked about the loader before. If you double click an executable, the Windows loader maps it into memory and loads all the imports that the executable needs to be executing, which in this case would be kernel32.dll and msvcr110.dll. And again, yeah, these are the functions that are imported. What's cool about Pro is that I could just say, I am interested in a specific function. Say, here we go. I want to know how many printfs are being called in the application. So go to the import table, I look for my printf import. This is not what I wanted. Okay, so your focus needs to be on the IDA view. Then you can double click in the imports and you're taken straight to the import table. I did not actually know if I'm in the hex view and I double click on printf, I'll land in the hex view. That is weird. So make sure that your focus is on the IDA view. First tab, go to the import table and then double click on printf. You land in this pink section where it says iData. So here you see everything that's pink in the IDA Pro. This is on the output. That is imports. This whole section starting at 14.00.2000. That's where our import table starts, and you see one import listed after the other. By the way, all the text that you see in IDA Pro, like the function names and these code references, the cross references and extern and keyword and all these analysis results, all the text is something IDA Pro came up with. Any function name, any variable name, any comment, anything that you see written is analysis work of the tool, which again means that it can be wrong if IDA Pro made a mistake about the analysis. In our case here, that's very unlikely because the executable is so small and simple and doesn't try to hide anything. But if you look at malware, it happens often enough that the malware tries to hide things. And the easiest way to hide things from an analyst is to throw off analysis tools. And I personally think that anti-disassembly is the meanest thing to do. Like if the assembler doesn't give me the right assembly outputs, then I will have to start reverse engineering on the bytecode level, and that's where it gets really, really ugly. That said, okay, what did we want to do here? We're in the import table. The import table is kind of cool in IDAPRO because I have cross-references listed. What is a cross-reference? Cross-references tell us where a specific item was used in a disassembly, according to IDAPRO's analysis. Again, this is all cosmetics here. Cross-references, for example, can help us find where a specific import was used. So if I click on this printf down here, this is a comment, yeah, you click on this printf down here, and you press X. X stands for cross-references. Then you get this list of all the calls to printf that happen inside of the application, which is a lot. I was expecting 2, whatever. Something that I mentioned before, you have like these bluish green functions listed in the function table. Again, here the pink lines are the imports. As you see in this pink section, so all that is pink is external symbols like imports for IDAPRO. And the blue stuff is library functions that are compiled into the binary. There is it boils down to different compiler settings of whether a compiler decides to link operating system code through the import table, or whether it imports the very code of a function and places it into the binary. There's a difference between static and dynamic linking and compiling. And for us, that means we are heavily dependent on auto-analysis. What do I mean by that? If you look at the function list on the left side, I can tell you that the application we're looking at does not have more than 6 functions. Like all that you see up here, like from the string line up, all of that is the functions that are written by me, like that the application developer wrote in the C code. And everything that's below is code that the compiler put into our program. Again, all of these bluish lines here, that's operating system code or like library code. Why do we need that whole stash? That whole stash is called C runtime. The C runtime makes sure that our application can start execute. So your Windows loader maps the executable into memory, and then the first thing we execute is not the main function. The first thing we start executing, where the entry point is pointing to, IDAPRO dubbed start function here. We can have a look at that in a second, with how the start function looks like. Usually that's not something we want to analyze. Usually the C runtime is not very interesting for the reverse engineer, but we want to analyze the application code, which is why it's very helpful that IDAPRO does this auto analysis and automatically renames the things that look like library functions to IDA. IDA does it with a set of signatures. So your IDAPRO installation comes with signatures that match functions that try to identify the tmain CRT, the C runtime startup function. And if it finds a piece of assembly that looks like this startup function, it will automatically name it that way, so that as analysts, we don't have to analyze it again. Reverse engineering is very time consuming, and anything a tool can do to save us time is very much appreciated. I know this funny story of a friend of mine who's a reverse engineer also, and at some point in his career, accidentally reverse engineered the MD5 hash function because there was no auto analysis telling him that this is MD5. And in that case, you can see what this analysis actually helps. Like if there's a function name coming back from IDA, we can go ahead and look for documentation for that function name. We can look up what is this particular function supposed to do, and then we don't have to analyze it, which is very helpful if you look at MD5. Like the MD5 hash function is actually not simple. Good. Where I was going with that. Right, that stash of functions here. There is a little peculiarity in the cross references, where if you look, you have every entry in here double. Here's the 1000 plus 43, and then here's the 1000 plus 43 again. So it's actually just half of that stack is cross references to printf in the function, in the binary. The reason for that being is that it shows us different types of these references, where there is type R and type P. I think R stands for read. I'm not sure now what P stands for. Pointer? I forgot. But for us, interesting is that there is this many cross references to printf in here. And in terms of clicky, it doesn't really matter whether you double click on the R version or on the P version. If you double click on any entry in the cross references, you are taken to this particular call to printf that the address indicates. If you want to know the address, again, you can click the space bar and you see the actual virtual address of that one instruction that we're looking at. If you find out this was not the printf you were looking for, you click on printf again, click X, and you see a list of cross-references again. And this way you can walk through all the different cross-references to a given import and see whether you can find the code that you actually wanted to see and wanted to look at, which is very helpful. Doing so, let's see whether we can find the hello world. Oh, there's a lot of printfs in here. Interesting. 1050 is not our function. 1250. Excellent. So if you look at this stash of printf cross-references again, there is one function that is called sub underscore 14,01250 plus b. If you double click on that, you find the hello world function that I mentioned before in the dropdown. And it's very similar to the one we looked at the Code Explorer. By the way, last time I forgot to give you your homework. What I wanted to tell you to do is have fun with the Compiler Explorer. That was my mistake. Yeah, what I'm thinking you should do, which is fun, is navigate to that. Not now as a homework after class. Navigate to the godbolt.org Compiler Explorer. Practice your C coding and look at what the compiler spits out for different pieces of code that you put in there. I'll talk about that again at the end of the class. Don't let me forget. We need homework. Because then what you can do is you can go to the Compiler Explorer and write your own hello worlds and maybe use different optimization settings and maybe use different compilers and compiler versions and see whether they spit out different hello worlds. You can put in like a simple loop, or you can put in a simple switch case or an if-else statement and see how the resulting assembly looks like. Yeah, that's rather fun. Okay, so we did imports, we did cross-references. By the way, cross-references work on any constant or variable, as far as I know. So for example, if you want to know if there's another reference to our hello world constant, you can click on the hello world, you can press X, and you will find out there's only one mention to that string in the binary, which is exactly here. Boring. We can do that on functions. If I click on this function and press X, I see that technically I have two cross-references, but the only interesting one is the first one, where it says main call sub underscore nana. This is where the main function calls the hello world function. There's also a runtime entry for this function, which is very much not interesting right now. Okay, imports, cross-references, hex view, instruction view, exports. Let's have a quick look at the exports table as well. The exports table here looks very boring because there's only one entry in there. The other executable I gave you, the SQLite3.dll, is a DLL. It's a library. The one major difference between executable and library is that the executable has one entry point. The loader loads it in memory, puts the instruction pointer to the first entry point, to the first instruction at the entry point, and starts executing from there. A library function, as you might gather, does not have one single entry point. We're going to look at the DLL in like this DLL's exports later on, and you will see that there isn't like one entry there, but a whole list of entries. If you write a library, you define a certain list of exports. Like a library is there to provide functionality. And out of a library, you can call different functions, different APIs. And you can only call the ones that it exports. Okay, and these exports are listed in the export table. Likewise, if you double-click a DLL, the DLL doesn't actually execute. There is a DLL main, like there is one main function that is loaded when the DLL that is executed when the DLL is loaded, but it's nothing happens if you double-click it. Like if you double-click a DLL, you can't actually execute any code that's in there. You might have noticed. More about that later. For us, if you look here, the one export we have, the entry point, is pointing to a function named start. This is something I mentioned before. You see that in the function list over here as well. There's a function called start. And now if I double click on this main entry, as it says here, I land in the start function. The start function is the first thing that executes, but it's not our main. It's not the main function the developer wrote. Start is just what kicks off the C runtime, which sets up the environment for our main, or like for our code to execute. And there's a jump to T main CRT startup. If you double click on that, you get to this big stash of code that is not very exciting to analyze. And somewhere in there, you find a call that takes us to the actual main function. Main here. Okay, so what I did, I started off in the start function where there's a jump to something called CRT main. And in that CRT main, usually somewhere in the center or bottom of the graph, you find a call to the actual main. If I double click here, I get back to that main function. It's not obvious, but I'm telling you that this is the function that I declared my main function in the C file that I wrote. I'm showing you this because sometimes IDA or some disassembly frameworks, they do not take you to the actual main function. They point your start screen to the start function. And I remember when I started reverse engineering, I was crazy confused about how to find the code that I actually wanted to analyze. And I was stuck in that CRT main, like the T main CRT startup function for a while, trying to figure out where's up and where's down. Again, if you're a beginner, then all of this here looks Chinese to you, which is totally fine. It's supposed to look Chinese. And then knowing where's upside and where's down and where's main and where to go from there is very essential in order not to get lost inside a binary. And that might just be me. If you feel different, then that's totally up to you. But I hated the start function. It's so misleading because it's called start, and this is where the entry point is pointing at. And then when you're in that function, you don't see code, right? Yeah. Okay, this was our introduction to IDA Pro. Now let's look at assembly together and go back to the slides. Oh, by the way, something I forgot is that color bar up here. That's something very peculiar. there's a menu here that explains like what the colors mean. It's in the like library function, which is the blue ones, like the light blue ones, and the regular functions, which is the application code, which is dark blue. Brown is instruction, which I think means that there's something not analyzed as a function. Then we have data unexplored, and pink, which is the external symbols. Function and unexplored. Whatever. What's cool about that bar is that you can click in it. It's not always very useful, but sometimes, like for example, if you quickly want to get to the import table, you click in the pink box up here and you land in the import table. If you click back in the blue box, you land somewhere in the function tab, in the function area. And if you click at the key stuff, you land in the library functions. You can also pull it up and down, that way scroll and have fun until the end of days, just scrolling things. Okay. Anyhow, I'll leave IdaPro here, but the focus on main. We're gonna get back here in a bit. Slides, where's slides? Here's slides, Chrome. Okay. Naturally, if you can't read assembly, then staring at the assembly output of any given disassembly framework is confusing. And I'm telling you now, I cannot teach you how to read assembly. That's something that your brain needs to wrap itself around by itself. I can teach you a few little tricks and can explain what a couple instructions mean. But from there, we're going to go and actually read assembly together. And you'll have to believe me the stuff that I tell you and eventually pick up the assembly yourself and start reading yourself. Cool. It's 9:12 here. Maybe it's a good time to actually ask whether you have any questions that I should answer. I just opened the chat here. Yeah, if you have any questions, please start ahead. I'll pick out some that look answerable right now to me. And again, if you have any questions after the class, just text me on Twitter, like send me a DM, and I'll be happy to answer. No questions. So silent. Okay, saves us time. All right. Where was I? The slides. The slides. Here we are. Really, no questions? Thank you. I love to talk my mouth fuzzy about hex dumps and disassembly and disassemblers. Also, you might have noticed I did this introduction to IdaPro a lot of times. In any class I teach, I tell people how IdaPro works. This is not to advertise IdaPro. It's just, again, for beginners, the easiest entry to analyzing binaries. Ghidra is just as great. I haven't used it all that often, but again, the disassembly output is awesome, and automation in Ghidra is great. Like you can actually script it. If you've ever tried to script IdaPro, it's a pain in the, yeah, you can imagine what I was gonna say. And then there's different other tools actually, like the tool landscape on the reverse engineering sphere is rather thin, but there's also Radar 2. Radar 2 is very cool. It's very versatile. It's a little buggy occasionally, but the developers are quicker in bug fixing than you are in fixing out what the bugs are actually. And I loved working with them a lot. They're a funny crew. Anyhow, again, for beginners, you need a tool that shows you data correctly, that recognizes function offsets correctly, that recognizes virtual tables, that recognizes string constants. Sometimes you see a disassembler thinking a string is executable code and actually not finding any valid opcodes there. So the disassembly just goes on and on and on, but it doesn't make any sense. That's when the tool messed up. Anyhow, let's go on. before we run out of time again. Memory manipulation in assembly. What you see when you look at assembly is like, imagine your code, you write 3 lines of C code that in the end is translated to 30, not 30 is an overstatement, like let's say 15 lines of assembly code. That is because in every line of code you write, there's so much stuff happening that the CPU needs to perform before continuing to the next line of code. And for us as humans, it means that the assembly that's spit out isn't exactly readable as the code would be. So if you read C code, you read from left to right as its normal text and from top to bottom. If you read assembly, you still go from top to bottom, and sometimes you go from bottom to top, and sometimes you start in the center of a graph, sometimes you start at the bottom of a graph, and the instructions aren't always very intuitive, and sometimes they're out of order. So again, if you read C code, there's one line after another, and once it's compiled into assembly, the compiler might have decided to move a couple instructions up or move a couple instructions down, like interleave instructions, if that has any performance gains for the executable code. And then it becomes like an Easter egg hunt to trying to figure out, okay, so here is a function call, and I'm looking for the arguments to that function call. So I look for the call instruction, and from there up, I look for the specific instructions that show me that arguments have been pushed to the stack or to registers. So that can be a little confusing. Memory manipulation, why is that important? We need to know how the assembly flow can modify things as execution moves on. For example, now let's start here, the first line, instruction plus operand. We have instructions that come without any operand at all. That, for example, would be a NOP instruction. NOP stands for no operation, and it's one instruction that does not receive an operand and also effectively doesn't do anything at all. There's other instructions without operands, like if you look at, I'm thinking VMX on might be one. Anyway, if you look through the Intel manual, you'll find a lot of instructions that come without operands. The instruction by itself performs all that it needs. More common though is an instruction with an operand. And if we look at operands, there can be immediate values. Like in the first line, you see 6E. That's an immediate value. It's a numeric constant that's hard-coded in the binary. We can see registers, which is a little more common, where you see here RBX is a register operand. RCX is a register operand as well as RAD here. So that's all register operands. And then you have memory addresses, like memory identifiers, let's put it like that. There, in the first line, you see a virtual address. By the way, these are just the most common memory access or memory manipulation activities that you can see in this assembly. So here is the dereferentiation of a virtual address. Something that might be a little confusing in the beginning, but becomes very natural after you read a couple of binaries, is to notice these edgy brackets. And an edgy bracket in this assembly means that we dereference what is inside of the bracket. Not in all cases, just in most cases, to make it more confusing. But usually, if you see an address or a register plus a register plus an immediate, that usually means that these brackets cause this address to be dereferenced. What does dereferentiation mean? Dereferencing a pointer means that we grab the value that's held at the location of where the pointer is pointing to, not the pointer address itself. The pointer address itself is a value, but if we dereference that value, we reach for the content of that specific memory location. That, if I put it like that, might make a little more sense if we quickly switch back to the disassembly tool. If you follow me to IDA Pro and we look at the hex view, If you look at that hex view tab, on the very left side, you see an address. This is the address that we're looking at in memory. These are 16 bytes, by the way. And you see, like, with every line, we advance by 16, which is like a 1 0. So 1 0, 2 0, 3 0, 4 0. This is like 16 plus 16 plus 16 plus 16. And these addresses here, theoretically, they are, I mean, this in that case is not a pointer, but if we had a pointer of the value 14,1240 and we go dereferencing that pointer, we grab the data that is pointed to. So say we grab a quad word from that address, what we get is these 16 bytes, the 83 until the CCCCC. That's what pointer dereferentiation means. Most people who have written C code know what a pointer is, and that the pointer can point to certain values. But then understanding how exactly that works in memory is still a little alien for most people, as far as I learned. And we will have to deal with that in the assembly later on a lot. But just internalize right now, if you see edgy brackets, most likely that means that we're dereferencing a pointer, and what will land in the target? Where are we? What will land in the target, like here in this line in REX? After this instruction executed, what we hold in REX is the value that is located where this pointer is pointing to. In that case, it's probably a 16-bit value, 64-bit value of 16 bytes that we load from there. In either disassembly, often enough, there's like a data width indicator, which tells us whether we load a word, a D word, or a quad word. That is helpful when reverse engineering. Yeah, and the same dereferentiation works with registers. In this case, REX holds a virtual address like this one, and the brackets mean that we dereference whatever is held in REX and load that value into REX. Looks a little weird, like why would we use REX here and here again? This is a pattern that's very commonly seen when you resolve structures. Might see that in the exercises. So imagine you have a C struct. C structs are like little blocks of memory, like imagine like a square. And that block of memory has an address. And the values in that block of memory have addresses too. So imagine a pointer to that structure. And from that structure, you want the first entry, like the first variable. Let's be an ID or something that you want to load out of that struct. Then what you do is you load the address of that struct into REX. And by dereferencing the address of the struct, you get the first entry in the table. In larger applications or in operating system code, what happens is that your structs are very big, and resolving a specific value in a specific struct can take a lot of different instructions that are executed and loading values from X amount of memory addresses, and it can get very confusing very quickly. Then it's important that we're able to read our dereferentiations. Okay, finally, the same thing works with the calculation. So you can have an address in RBX and an offset in RDX and add another offset to that offset, and this way calculate, again, a virtual address that is then resolved, and the target of that resolving pointer is loaded into REX. Okay, I say usually these brackets mean dereferentiation. There is one case where that might not be true, which is the LEA instruction. I am not sure now. This is the only case where the edgy brackets don't mean dereferentiation. Usually, if you have an LEA instruction, LEA stands for load effective address. LEA is used for calculating addresses rather than dereferencing them. And it also uses these kind of brackets. If you have an LEA, RAX, and then this, what lands in REX is not the location where the resulting pointer is pointing to, but the result of this calculation. LEA is just a fancy way of saying add RBX RDX, add RBX 10. If that makes any sense. And we will see an LEA instruction in the exercises. I'm pretty sure about that. All right, this much about memory manipulation. Heap. I will not be talking about the heap at all, pretty much. I say this because there is like books and books and books and books about memory management on different operating systems and how the heap is organized and so on and so forth. And if you're statically reverse engineering binaries, you don't care about memory management that much at all. Something important is that when we're loading a binary, we're looking at the virtual memory, like at the representation of that binary in virtual memory. That is not the same as physical memory. On modern operating systems, executables, once they're running, by the way, an executable mapped into memory is typically called a process. When a process is executing, the process thinks that it has the whole virtual memory, like on 64-bit systems, that's a very big space, that has this whole space by itself. That space is definitely bigger than the physical memory that the computer has in RAM, like the RAM chip that is in the computer. The concept of virtual versus physical memory, like the concept of virtualizing memory, allows us to use a much larger space of memory than the computer has physically present, like has physically inside of it. And yeah, this is the way we separate processes. Resource management is one of the reasons. Security is another reason. So a process that messes up its own virtual memory does not mess up the rest of the system. If you're as old as me and you have used Windows 95 at some point, you might have noticed that Windows 95 used to crash a lot, which wasn't necessarily the operating system's fault, but also the issue that there was no separation of like security spaces on Windows 95. So if you had one process, like a random application that you ran that would corrupt its own memory, that could potentially tear down the whole operating system as it was running. Which is why eventually we came up with user land and kernel land and the separation in there, and practically sandboxed our sandboxing is the wrong word, like try to separate our running processes on Windows so that one process couldn't kill all the others at the same time. Which is a very high level and a rather confused introduction of virtual memory. If you're interested in that topic, please again look up resources. There is a lot to read about this particular topic, and there's a lot of research going on in the area, and it's always very exciting, but it's also a lot to wrap your head around. For us today, what's important about the heap, and especially dynamically allocated chunks of the heap, is that this is usually how our application gets access to larger chunks of memory. That I mean buffers. And generally, so that also depends on what your compiler thinks about your source code. But generally said, memory that's allocated with a malloc function or any other given operating system provided allocation API. Generally, those functions deliver chunks of heap. They allocate little bits of memory in the virtual memory space of the computer, of the process. As opposed to that, generally what happens if you define a regular variable, that variable is typically held on the stack. So if you define a couple of integers and if you define a couple of strings in your function as you write it, and they are statically defined, like they're constant in that specific function, they usually end up being stack variables. Yeah, as opposed to allocated memory. What's also interesting about a heap is that we have one heap per process, as opposed to stacks. For the stacks, we have one stack per thread. Process, again, is that execution unit as the operating system sees it. If you double-click Microsoft Word, you have a running Word process, and that process can consist of different threads. The threads, in the sense of execution, have their own little environment as well, but they all live in the same virtual address space of the running process. They do have, like a thread does have its own stack. So every time we do a thread switch, the stack pointer is switched in the process, and yeah, the heap does not change. So the buffers we have in the heap remain valid among the different threads. But you can imagine a local stack variable might not, because the stack changes. Anyhow, let's move on to the stack. We could talk for hours about heaps. Actually, once I did this slightly masochistic adventure, I started reading a book about Windows 7 virtual memory, about the Windows 7 virtual memory manager. I got about halfway through and then I gave up. It was just too obscure. Like, we all work on modern day operating systems, but the way they deal with memory is something that's incomprehensible for a living human being. Or at least for me it was. Okay. The stack is a somewhat slightly more important piece of memory as we go reverse engineering, because the stack is what holds all our local variables, like the data that's being used inside of a function, if it's not located on a heap. And it also defines our function boundaries, because the stack is where the function stack frames are managed. When reverse engineering, that's mostly important for us to be able to identify what is a variable, what's the size of a variable, what is an argument that's handed to the function, and therefore we need to understand how stacks work. Again, we have one stack per thread. If we have a multi-thread application and the threads switch, like we have a main thread and a child thread, and the child thread starts executing, it gets its own stack. Yeah, push and pop are our favorite instructions to interact with the stack, but actually I think it's more common to directly access stack variables in the assembly. You'll see what I mean in a second. Yeah, stack is provided by the operating system. It's a LIFO buffer. What does a LIFO buffer mean? Also, Rsp and Rbp come into play here. Here on this slide, I have a very abstract depiction of a stack. Imagine push and pop mean that you push a value on the stack, and you push another one, and then you call pop, and the topmost value is popped off the stack. Typically, when you call a pop instruction, then you have pop and an operand, like a register. I'm pretty sure you cannot pop a value into memory operand. I would have to look that up, but usually you have pop register. And then what happens is that by executing that pop instruction, the topmost value of the stack is loaded into a register. That specific register, that is. And again, yeah, this way your stack goes growing and shrinking. That's the most basic way to describe it, though. What's important in this graphic here is that we have a base pointer and a stack pointer. Rbp stands for base pointer, and Rsp is the stack pointer. And a function, when it's executing, is living in its own little world, in its own little cage. And that cage is it's not a cage. You can access outside of your function stack frame, but for the functions as they're implemented by the compiler, they rely on their own little stack space to be there for it to use. And that stack space is managed by these two pointers, base pointer and stack pointer. base pointer points to the base. So at the beginning of a function, the base pointer is set to the current location on the stack, so that it points to the base of the stack frame. You will see in a minute that that is not entirely true. Like there's parts of the stack frame that are below the base pointer, and then there's parts of the stack frame that are above the base pointer. But the base pointer is typically the base if we try to address anything in the stack. So Rbp plus 10 moves us 16 bytes up the stack, and Rbp minus 10 moves us 10 bytes down the stack. This is how arguments and local variables are managed in the stack frame. And the stack pointer is used to point to the top of the stack. So as the function goes executing, it might be pushing things onto the stack, and the base pointer keeps pointing to the base. So it's not usually modified, but the stack pointer keeps jumping up. Interestingly, that is something implicit that happens. If a push instruction is executed, the stack pointer is automatically decremented because we grow downwards. Anyway, so the stack pointer moves automatically when we execute a push instruction. Simultaneously, if we execute a pop instruction, the stack pointer moves down the stack, and that is not an explicit operation. What you see here, there are some instructions in Intel architecture that have side effects. So if we execute push, the stack pointer changes. That is something architecturally defined. That's not what the compiler does, and definitely not the developer. That's the CPU that automatically performs that operation. And there's a couple of other instructions. There's actually a lot of other instructions that have these kind of side effects as well. So for example, if you execute a call instruction, you call a certain address, and at the same time, the call instruction pushes the return address on the stack, and by doing so, also increments the stack pointer. Decrements, sorry, we grow downwards. The stack grows downwards. Anyway, so you see you have different instructions with their side effects. And as you go reverse engineering, you need to be aware of those side effects. Otherwise, things might not make a lot of sense to you. Yes, but we're going to be looking at assembly at some point, hopefully. Calling conventions and ABIs. The reason why the stack is so important is because we need to understand how functions are implemented on the Intel architecture. Calling conventions and ABIs are something compilers define. Like the ABI, the application binary interface, defines how binaries want to be interfaced with. In a sense, that says how a certain function asks to be called. In C codes, all the function calls look more or less the same. And in the binary, there's different ways of calling a function, or at least on 32-bit, there were different calling conventions with different looks. And we're only going to be talking about one today. Just be aware that like on 32-bit Windows, there was a whole convention madness. Like there was a whole list of conventions, and that is sometimes confusing when looking at functions with different conventions. A convention in a binary calling interface defines how function arguments are handled, like parameters, how the function gets to use its stack, and which registers have special designation. I just told you about instruction side effects. So the stack pointer has a special obligation. If there's a push instruction executed, it needs to change its location, like change the location it points to on the stack. That means we cannot actually use it in an arithmetic operation. Like if you zero the stack pointer and load a random value in there, then your function stack frame goes lost. Like you can continue executing while referencing variables and parameters because your stack pointer is pointing to Nirvana. That's usually not what you want to do. That's just one special designation. Another special designation of registers would be that REAX or EAX is usually the return register. That is a convention. That is something that compiler defines for us. When you return from a function, you have one return value, and that is usually handed back in EAX. That is a special designation of your register. The calling convention defines which other registers have a special job and which ones do not, which means which ones can be used freely by the function without worrying about upsetting the flow of execution by changing the value inside the register. Okay, this is a lot of theory. How does it look in practice? Here's a little less abstract depiction of a stack. This is the classic 32-bit cdecl calling convention. Cdecl is ages old, and cdecl is the most common one, not the only one, but the most commonly seen one. And I think it's the simplest one, which is why we're going to be talking about cdecl for a bit. This is not how stack frames look on 64-bit, but it's a good way to start understanding how things look like on 64-bit. Cdecl convention is rather simple. It says when a function is called, the arguments that the function receives need to be pushed on the stack in reverse order, which means you have a call to a function and the function receives argument A, B, and C. What you see in assembly is the call instruction, and above the call instruction, you see push B, push C, push B, push A. Like in C code, you see function call ABC, and in the binary, you see the push C, push P, push A. So it's reverse order. Welcome to Intel. And this way we can reverse engineer the specific function call. Anyway, so what it means is that these arguments land on the stack in reverse order. And then what happens next is that we issue that call instruction. The call instruction, as I just mentioned before, pushes the return address on the stack, which means now the stack has the arguments, the return address. Then what it also does, it stores the old frame pointer, which is something I have not noted in that graph. The frame pointer of the old function is stored in the stack as well. And then from there, we start arranging local variables of the function on the stack. So if the called function defines an integer a and an integer I and an integer d or whatever, then those variables land on the stack as well. And that is the function stack that we have after we call the given function. Now, EBP is set to the top of the stack before we set up local stack variables. You see in the graph here, we had a function 1 with a stack frame and a function 2. So function 1 called function 2. What happens when the function is executing is that EBP is set to the top of the stack. That's usually a move EBP ESP instruction, so that EBP points to this spot where we can start executing with our local functions. I told you before, EBP is the base of the stack frame, but not exactly, because the stack frame actually extends to return address and function arguments that are pushed onto before. And what I forgot in here is to note that the old EBP, so function 1's base pointer, is stored on the stack as well, so that if we return from function 2, we can restore the old stack frame. We'll see that in the binary when we go about debugging function stack frames or function calls. Just now, for like statically reading assembly, it is important to remember that EBP and ESP are usually used to reference values. Usually that is values on the stack. And this here is a very simple version of a stack frame. Again, this is 32-bit cdecl when things were still clearly defined and not very well optimized. Yeah, and now we'll move on to the 64-bit stacks. Something I mentioned before, I will mention again, which can be confusing, is that the stack grows downwards. Again, welcome to Intel. Little endian is still a thing. The stack, like the memory view, the virtual memory, if we look at it, is upside down. The stack starts at a given address and then shrinks or it grows towards a lower address. So the addressing goes in reverse, which will be important when we look at sometimes a function allocate space for local variables. And allocating space in the stack is done by decrementing ESP. So you decrement the stack pointer, you generate space on the stack. Weird, isn't it? All right, this will all make more sense when we look at the actual assembly. This is just, once you've heard all of this, you have it in the back of your head. And then when we look at the disassembly and I say EBP minus 8 reference something that's on the stack, you'll be like, yes, base pointer, stack, function frame. Cool. Let's move on to the 64-bit. Oh, no, we don't. We have an exercise here. Just a very quick look into the future, because you see we're running out of time again today. On 64-bit Windows, we only have one calling convention. I needed to look it up myself because I couldn't quite believe it. I have reverse engineered 64-bit binaries before, and I never actually noticed that the calling conventions are all the same. Oops. Apparently on Windows, we only have one 64-bit calling convention. And that implies that this one calling convention is also rather complex. Remember, with 32-bit CDECL, our arguments were pushed to the stack, our return address was saved, our frame pointer was saved, and then we put our local variables on top. Okay. With the 64-bit version, we have a few updates to that. So first of all, arguments are not primarily handed over through the stack anymore because that is slow. On 64-bit, we have a lot more general purpose registers, which allows us to be a lot more generous with the use of registers. Mostly that means that the calling convention now relies on 4 registers to be used for 4 arguments, not more. If a function has more than 4 arguments, we still rely on the stack. On Windows specifically, and please note, on Linux that is different. Linux uses the System 5 calling convention. But on Windows, the first argument to a function is stored in RCX, the second argument in RDX, the third argument in R8, and the fourth argument in R9. If we're looking at integers, or any data type that results in integer in a binary, which can be a lot of them, anything that results in a floating point, which for us is not that interesting because we won't be looking at any assembly that contains it, but there's also XMM registers. We have XMM 0 and 1 and 2 and 3, which are used for the first 4 floating point arguments. If we have mixed integer and floating point arguments, it gets interesting because then these registers are mixed up. Like, yeah, it gets very outer space to look at that. Anyway, in a regular case, if we only have pretty normal integer arguments, we use RCX, RDX, R8, and R9. If we have more than 4 arguments, we resort to pushing the rest of them onto the stack. So argument 5, 6, 7, 8, 9, 10, whatever, however many we have, still land on the stack in reverse order, as is usual, kinda. Then there is this interesting bit about the 64-bit calling convention, is that we have a home space that is reserved for the register arguments on the stack anyway. So we don't push all of them onto the stack, but we reserve space for them to have on the stack, which is why the Windows 64-bit stack frames are a lot bigger than they are on 32-bit, just because we reserve so much more space in there. But again, on 64-bit, we just have a lot more memory at our disposal, so that's okay. Then REX, again, is the return register, or the designated return register, as EAX was on 32-bit. And if we have this call, like if we have C++ and a member function, then RCX, the first argument, will hold the pointer to the object of that C++ object. We won't be looking at C++ reverse engineering in this class either, so this is not all that important. Just something to have in the back of your mind. And Then we have volatile and non-volatile registers. Volatile means that they have use and as such cannot be freely accessed and cannot be freely modified by a called function. So if a function is called and that function needs to make use of rdx, for example, but rdx is holding an argument, then the value of rdx needs to be saved, and yeah, then rdx can be used. Wait a second, I'm mixing something up here. We'll see that in detail in the assembly later on when we see specific function calls. In the beginning, sometimes you see a lot of register storing, like a lot of push instructions that don't seem to have obvious use, and at the end of a function, a lot of pop instructions that pop values from the stack in the same order back into registers. That is because the calling function, like the one that called into the callee, expects these registers to come back from the call function with the same value they had before. I think I got that in reverse when I started explaining before. So when you call a function based on this calling convention, the caller does not expect RAX to remain unchanged. RAX is the return value and will be the designated register to hold that return value. So when the caller calls the function, REX might have a certain value, and when it comes back, it holds the return value, which is a different one. And that is okay because the caller knows that based on the calling convention, it cannot rely on REX to remain the same. That is not the same for for Rbp and Rsp, and RDI and RSI and RBX and R12 to R15. So these registers need to be unchanged, which means if the callee, the called function, wants to leverage those registers and store values in them and do calculations and whatnot, it needs to save them somewhere. Usually that's the stack. So these values are saved on the stack and returned in an unchanged manner to the caller. Rbp and Rsp are slightly special. As you saw before when I was talking about the stack frame, Rbp is saved on the stack and restored when we return from a callee. The callee has its own base pointer, so the base pointer is overwritten, which is why the old base pointer needs to be stored. And RSP naturally will return, should return to the state that it had before the callee was called. So at the return of a function, RSP and RBP are supposed to hold the same values they held when the callee was entered. Lots of theory here. Other x64 Easter eggs? Yay, we're done with the stack frames. That all said, it would be time for an exercise. This one most particularly. Okay, that was a lot of theory about stack frames. By the way, there is something I would like you to read. Your first piece of homework. There is a tab I have open here. Again, on the GitHub, there is a text file that says links and reading material. And in there, you will find reading material about the Windows 64 calling convention and Windows 64 ABI stack frames. I will not say you cannot reverse engineer binaries if you don't know how a stack frame works, but it's getting close there. Understanding of how values are referenced in assembly and what exactly is loaded if we dereference RSP plus 24 and such stuff. That can only be understood if you have a solid understanding of stack frames. And sadly for 64-bit, these are a little complicated. Therefore, I was going to ask you to read these two blog posts. They are not all that long, and they will explain in more depth than I can how 64-bit Windows calling conventions looks like. The website it leads to looks like this, with a pretty picture of the author up here. And what you see in there, among other things, is a nice graphic that depicts of how a 64-bit Windows stack frame looks like once it's on the stack. And you see it's a little bigger and a little more complicated than the 32-bit one. What this blog post also nicely explains is the different tasks of the individual pointers. Like here's a whole chapter on the stack pointer, on the frame pointer, on the non-volatile registers, on the local variables, on the home space and the extra parameters, the stack frame size. Here's an example. Optimizations. Yeah, essentially I would ask you to read until like here, stack frame size. That is some good theory. Yes. Yes. For us, I would love to jump into IDA now, but I think we're running out of time. Let's quickly, as a closing thing, let's go through this little example I posted here. This is again 32-bit CDECL, but it's a good entry exercise to work towards the 64-bit stack frames. On top, you see local variables and arguments. We and also analysis tools, like this is a thing I copy pasted out of IDA Pro. Analysis tools know that something is an argument because it's referenced with a positive value, and that something is a variable because it's referenced with a negative value. Positive as seen from the frame pointer. If you have a quick look down here, you have EBP plus arc0, which essentially means EBP plus 8. So remember, frame pointer points to the base of our stack frame. And with CDECL, all arguments are held below the frame pointer. So if I add something to EBP, I walk up the memory and down the stack. Remember, the stack is reverse. So adding things to a stack pointer, like the frame pointer or the stack pointer, moves you down the stack. As opposed to negative references, if you look at EBP plus var 8, that actually results in EBP minus 8. And that means we're referencing something above the frame pointer, like we're walking up the stack. Okay, that's local variables because they're at a negative offset from the frame pointer, and the others are arguments because they're at a positive offset from the frame pointer. Beautiful. Then, what is something very important to see in here is the function Prolog and the function Epilog. The Prolog stores the frame pointer on the stack, sets the new frame pointer to where the stack pointer is pointing to, and then goes and reserves memory on the stack, which in this case is 8 bytes, which is enough space for both our variables. Again, we're in 32-bit here, so every slot on the stack is 4 bytes big. Okay, Prolog and the Epilog is what resets that frame pointer. So we're resetting the stack pointer, and we're popping the saved frame pointer from the stack. So in the beginning here, you see the push. At the end, you see the pop, and this grabs the same value. That also means that all the pushes and pops inside of the functions that are executed need to be in balance. Which, by the way, is how IDA Pros, like how any disassembler frameworks function detection, like the simplest way of function detection works, is by following the development of the stack pointer and the frame pointer. If you see here, we start out like say at 0, then we add something, or like we move. How to explain that? Inside of that function, frame pointer and stack frame, like the stack needs to be in balance. If we execute pop BBP here, and the stack pointer, which controls the stack, is not pointing to the value that we pushed onto the stack here, then we corrupt our function stack. which is not usually what happens. So compilers take care of that. And yeah, essentially this pop instruction down here is granted to grab the same value that we push in the stack up here. And then we call it return, which takes us back to where we came from. And yeah, these are prologues and epilogues. And 64-bit prologue and epilogue look a lot bigger and a little more complicated, and we'll be looking at that. In here then, I'm already out of time, but I need to finish this. Start at the beginning. We have a call to a function which we see here accepts one argument. In ctecl, all of the arguments are pushed to the stack, and we only have one push EAX, we see here. So we know that this function accepts one argument. The argument, if we follow the assembly upwards, is arc0, like EBP plus 8, is the value we store in EAX and then hand over to the function that we're calling. Below that, we see cleanup of the stack. We add 4 to ESP, and if you add 4 to ESP, that means that you give away space on the stack. That's because this function here allocated apparently one local variable, which is why we need to clean up stack. The reason why calling conventions on 32-bit were so confusing, because they define like how arguments are handed over and how the stack frame is managed. And you could have different responsibilities distributed between caller and callee based on which calling convention a certain function was using. Yeah, this here is part of the calling convention to clean up the stack. And then here is bad optimization. Essentially what these three instructions do is store the return value of this function into EAX. After we return from here, EAX holds the return value, which is stored in a local variable. The local variable is loaded into EAX. So at this point in time, we still hold the return value of this function. And then we add argument 4 to it. So EVP minus 4. Okay. We have a function here that received two arguments. One of those arguments is handed over to a subfunction which performs some operation on it, and whatever is returned is added to the second argument that the function received. And then with this return instruction, we return whatever value is held in EAX. All right, cool. We just reverse engineered. And that very quickly too. I can absolutely believe that you guys did not understand everything that I was just talking about. Again, you're very welcome to watch the stream again and again, and you're also very welcome to ask me questions on Twitter in a DM. Now, to close this stream, are there any specific questions? Homework, good point, thank you. Your homework is go to godbolt.org, which is the compiler explorer. To remember what I'm talking about, that was this website. Write yourself some pretty code in here. If you will, go to the C file that I gave you and pick certain functions in there. They're very simple. They're also very stupid. And paste them in here so you can see the disassembly that is spit out. You can switch back and forth between GCC and Visual Studio, like the Visual Studio compiler. I would totally recommend that to get a feel of like how the different assembly looks like. And you can play a bit with optimization settings. Like if I say, does anything happen if I optimize this? Oh, yeah. Okay, if you tune up optimization to 03, all of a sudden your hello world looks way different. Anyhow, such fun, much wow. Godbolt. Yeah, and read the articles about the 64-bit stack frames. Not because you need to study each and every bit of the stack frames, but because I need you to have heard certain terms before and to develop some feeling about what the stack pointer and what the frame pointer are and what they do. So then when you look at the function and I say, oh, look, here we have a stack argument. Oh, look, here, the first function argument from ECX is loaded somewhere or pushed into the stack or something. You are not as confused, and I can go a little faster on the topic. All right, that all said, are there any important questions? If not, I would call it a day and start going to work. I thank you all a lot for the attention and for sticking around so long. And I hope to see you next Monday for when we spend a lot of time in IDA Pro digging through functions. Thanks, you all. Bye bye.